Hi, in this video I'm going to talk about beats, which is another interference phenomenon. Let's imagine you turn on some kind of single tone generator. So you're listening to a single note, a single pure tone, so just a sine wave like I've drawn here. This sine wave, you can see it up here, has a frequency of 12, like 2 pi ft, right? So 12 is number of cycles per second. That shows the amplitude to be 0.4 for no particular reason other than it fits nicely on the screen without too much messing with the axis. Alright, so as you can see, here's time 0, over here is time 1, and I can imagine this is the sound as it arrives at my eardrum, for example. Right, this would be the oscillation of my eardrum. In this case 12 times per second. I wouldn't be able to hear it. It's too low for me to pick up, but as an example, let's go with it. Right. So after 1, so 1 is right here, this graph will have done 12 full cycles, 12 full oscillations. Well, let's imagine I add to the single tone of 12 Hertz another tone that's 11 Hertz. So let me get rid of this one. Let me turn an 11 Hertz one. Right, here we go. Looks very similar, right? Difference is it only has 11 full cycles. So if I have them both arriving at my eardrum, right, and you get those two waves, the red one and the blue one both arrive together. So what's going to happen initially? Right, they're pretty much in sync. You can see because they're just barely different in their frequencies, 11 and 12. Right, they're almost the same period. Like the red one is just a tiny bit shorter of a period. So initially they're sort of in sync, and they're going to stay in sync fairly well. But over time, as we keep going, the blue one, which oscillates a tiny bit slower, keeps falling behind, right? So for example, the red one has done 2 full cycles right here. The blue one takes a fraction of a second longer. Right, it's a tiny amount. But over time, this tiny amount builds up. So by the time we get to about 0.5 seconds, like around here, the two waves, they're totally opposing each other. Right, so here they're going to cancel each other out because by the principle of superposition, positive displacement, negative displacement, if I add them together, it's going to cancel out. Then as time goes by, they're going to get closer and closer to be in sync again. So by once 1 second's over, they're again in sync, except the red one has done 1 full extra cycle, right? Because it's 12 Hertz versus 11 Hertz. So again, and then the cycle is going to start again, right? So then next second starts, and the blue one is again falling behind just a tiny bit. So what does it look like then? It looks like here they're constructively interfering. Over time, it's sort of somewhere in between, and at 0.5 they're definitely destructively interfering. Let's actually write down, see what they look like together. So I'm just going to add the two. I'm going to take this one here. I'm going to add to it the second one. So here, let me turn those initial ones off, and now you can see what it looks like, right? So initially, really big, 0.4, constructively makes 0.8. But then, as time goes by, it's still fairly constructive, like they're still adding up somewhat, just a little bit out of phase. But when you're right in the middle here, they're canceling each other out, or very close to it, and then they start getting closer and closer to be in sync again. And that cycle repeats, so when I zoom out, right, it's gonna sort of look something like this. I mean, what you can tell that in this case, I have exactly one loud, one quiet. So this would be loud around here, quiet here, loud here, quiet here, loud here. Right, one loud, one quiet per second. Like from 0 to 1, it is loud, goes quiet, loud, loud. So it's always 1 second from loud to the next loud to the next loud, or 1 second from quiet to quiet to quiet. Why 1? Well, it's going to turn out that it's exactly the difference between those two. It's going to determine how quickly these these waves build and shrink and build and shrink. But what I would hear is getting louder and more quiet once per second. This is a phenomenon that is called beats. All right. Now we could derive this. I could derive this on paper. Instead, I'm going to be lazy here and just show you the textbook derivation. So if we go to textbook here, right? So this is section 17.8. So this is the displacement, right? So principle of superposition says the displacement d is the sum of the two. Now I picked my a, my amplitude, to be 0.4. And I had omega 1, omega 2. In my case, they were 12 times 2 pi and 11 times 2 pi, right? Omega 1, omega 2. Slightly different. So then, the trick is, we're going to use the following trick identity, right? Remember trick identities, we've used them before. They're kind of one of our physics toolbox tools, right? You just have to you know they exist, and maybe sometimes you want to remember that they're useful. So, there's this identity that says the sine of alpha plus beta, any two alpha, is equal to twice the cosine of the half their difference times the sine of half their sum. So here we've got the sine of one, sine of another. So alpha is omega 1t, beta is omega 2t. We use this identity, and what you're going to get is this, right? So now I have d is twice the amplitude times cosine of a function that oscillates, right? It's a cosine function of time. It oscillates with an angular frequency that is half the difference of the original two angular frequencies. So let's visualize that. In our case, the angular frequencies were 12 times 2 pi and 11 times 2 pi. So the half of the difference between them would be, well, the difference is 1 times 2 pi, 12 minus 11 times 2 pi. So 1 times 2 pi over 2 would be pi. So in our case, this part here, this part here, including the half, would be just pi, for the example that I showed you on the graphing tool. Right, to make sure you understand the algebra here. And then this times the sine of 1/2 times omega 1 plus omega 2. So this is just the average of the two angular frequencies. Right, so in our case, that would be the average of 12 times 2 pi and 11 times 2 pi would be 11.5 times 2 pi. So in our case, this would read sine times 11.5 times 2 pi t. Right, so and this difference, this half times the difference, is called the modulation frequency, the modulation angular frequency, if you like. Now, what does this all mean? So, this cosine function, right, changes very slowly because this is a very small number. Right? In our case, it would be 1/2 times 2 pi. It's the difference, half times the difference. So this is a very slow cosine function. And then this is a very fast sine function. This is essentially the average of the initial two incoming ones. So if I plot that for our case, right, I did it here. It's exactly what the equation just says. I have twice the amplitude, 2 times a, then 1/2 times the difference, and then times sine 1/2 times essentially the sum, so this whole thing is just the average. You can see right away I get that same shape that we just saw plotted here as explicitly the sum of those two functions. Now, let's take just the cosine function. So I want to have the same function again, but I want to ignore the sine part. Like the sine is the fast oscillation. So here's what we get, right? I get this shape that just traces out the essentially the amplitude. Yes, with a plus or minus, like above and below, but it doesn't really matter, right? So the sine function is the red oscillation that's fast, and the cosine function, the amplitude, is essentially the gradually changing amplitude of those fast oscillations. So it's loud, quiet, loud, quiet, loud, quiet, and so on. And what you can tell from the math is that this modulation frequency, that's the where is it, the blue line, right? That is essentially a half times the difference, right? So if the this is expressed in terms of the angular frequency, of course, but if I just divide by 2 pi, I could also say that this modulation frequency f mod would be just the average, so the half of the frequency difference. Right. So the frequency of the blue function is a half times difference between 12 and 11. So the half of 1, that's a half. Let's check. Indeed, it takes 2 seconds for this function to go from to complete one full cycle, to go from say a maximum to the next maximum. Right, so half times the frequency difference. That's the frequency of this modulating function, this envelope function. So, but because within one full cycle, this function goes to 0 twice, once here, that implies the number of beats per second, meaning the number of loud and quiet, is twice the frequency of the blue function, right? It's once loud here, and it's once loud here after the blue function is done half a cycle. Because the oscillation doesn't care whether you are down here or up here. So the upshot is then that the beat frequency, like how often per second does it get loud and quiet, that is again just the difference between the two incoming frequencies, 11 and 12. So that is the math. Now, of course, those are frequencies that are way too low. Let's see what it looks like if we pick more realistic ones. So let's say I'm going to go from 120 and maybe say 118. Sorry, say 118. Right, those are my frequencies now. Those are fairly low notes, but notes you can hear. Let's plot those. So they're too fast to see. I mean, you can't see anything here. I can zoom in, and then you can sort of see. Here's the red one. Here's the blue one. They look fairly similar, right? You can sort of see that. You almost see like patterns in this, based on whether they're constructive or destructive. So maybe there's some, somewhat trippy visual experience here. But if I add them, what am I going to get? Well, let's add them. I'm going to end up with this. Oops, what have I done? I haven't fixed this one, have I? I forget, it didn't look quite right. 120 and then 118. There we go. Much better, right? So you can see the same sort of pattern. Lots of oscillations. Those are the essentially determine the pitch that I hear, the frequency of that, which would be 119, right? The average. And then I get, so the difference is 2 hertz. So that means I should get 2 beats per second. Let's check. So there's 1. Now we're at 0.5, and then 2. Okay, now we're at 1. Indeed, that works out. I can check it here too. So make this 120. 118, this 120, this 118. I get this. Of course, when I zoom in, I can see the individual oscillations here, but from afar, I can just see it's loud, quiet, loud, quiet, loud, quiet, and then the tone I hear, the actual frequency I hear, are these fast oscillations. And again, the envelope function, if I give it the right values, looks like this. And I mean, that's pretty much all there is to beats. You need to understand the math, right? But it's very short. It just uses a trig identity. That's the trick to it, right? But beyond that, there isn't much to understand here, right? You want to understand the phenomenon, and you can make this happen. And in your lab, you will already have made this happen. Essentially, you can just do it in a computer. You essentially open up 2 tone generators. You can just search for tone generator online, and you get all sorts of little browser-based programs that just generate a note. And you pick 120 and 118, or maybe let's try. Let's stick with this one here. Let's try 100 and maybe 440 and 443, right? So now we're off by, what am I doing? This is wrong. This one's meant to be 443. And here's 440. Oops, 3. And it looks like this, right? The same idea. You can't see the individual oscillations unless I zoom in really far, like this. And so 440 is the note A that orchestras tend to tune to. So the A just below the middle, so it's called the middle C, especially if you're a pianist. Now we could play a little game here, and maybe let's go back to this one. Ask what happens if the if the amplitude isn't quite the same, right? So here it's 0.4 and 0.4. Maybe you wanna think about this first. What happens if the amplitude of the two waves isn't quite the same? Let's have a look. Let me turn this one to 0.6. So what you see now is, again, they do the same thing, but because they don't quite supply the same amount of oscillation, it never quite goes down to 0 all the way. So in that case, what you would hear is loud, quiet, but not actually moments of silence. So again, make sure you understand that part, but that is what there is to beats. But it's a really fun little phenomenon. It has applications. If you want to tune a piano, for example, you can use beats to say, listen to one note and another note, or you want to tune your instrument to a reference note that somebody else is playing on a different instrument. So if you've got really good hearing, or you've got really well trained hearing as a musician, you can use beats to fine tune your instrument, so you're exactly at the right frequency. So applications for it there. There are others too. There's some problems in textbook that have some other applications. It's very simple, but really quite a little fascinating topic. Anyway, thanks for watching.